So the goal of these lectures were to serve a bit as an introduction and, well, of course, basically, for the first workshop that we're going to have which is going to have sort of a geometric aspect. So it was meant to give an idea that there's going to be several talks that are related to what I speak about in these lectures. So, okay, basically everything that we've been discussing in this program so far was one way or the other about functional inequalities. Everything could be viewed somehow in that setting. It was largely for Boolean functions defined on, for 0-1 value functions defined on various domains. Now it's going to be philosophically the opposite about functions with values in infinite dimensional Banach spaces sometimes. So a bit of a different philosophy. But again, something which happens a lot in analysis is that you have functional inequalities that when you restrict them to some very special classes of functions, they give you qualitative consequences, right? So it hasn't appeared so far, but Talleyrand's influence inequality or the L1, L2 inequality, you restrict it to Boolean functions, you get KL. Or from another field, you take the Sobolev inequality, you restrict it to an indicator function, you get isoperimetry, or some common geometry. So you restrict Prokop line to indicator functions, you get Minkowski. So there's this philosophy of restricting, importance to very special functions, more structured ones, and getting geometric or qualitative consequences one way or the other. And that's partly the goal of this lecture. So the goal is to devise functional inequalities which would be valid for all functions of the form f from v of g into x, where g is a graph and x is Banach space or metric space for parts of the curve. So devise inequalities which are valid for every such functions, which let's say guarantee that G cannot be reasonably embedded into X. Okay. So when we find inequalities which are valued for functions defined on a graph with values in a Banach space, such that from them we can deduce immediately almost that f, the function, could actually not have been a very good embedding. Okay. And okay, the bad thing about this is that this is a very case-specific problem, depending on the graph you're given, not on the space very often, but that's also the good thing about it, because we have things to do. And we are going to try to solve this kind of problems for various classes of graphs and for spaces with given properties that we hope to be able to compute. And this is really a place where analysis, probability, combinatorics, even group theory interact very well. So let me give the first definition of what reasonably embedded would mean. And I should say somehow, this is really going to be a mini course in the sense that a lot of the things are classical. I don't think that today I'm going to make it to the 21st century. It's really going to be classical things, not necessarily simple, but classical. So we say that the metric space M embedded with bi-Lipschitz distortion at most capital D, which is a number greater than 1, into a different metric space. And if there exists a mapping F from m to n, and a scaling factor s such that for any x and y in the domain, if we want to compute the distance in the image, so if we want to compute the distance in n between f of x and f of y, it's bounded between two multiples of the distance in the image. It's bounded below by s times the distance in n, and bounded above by d times s, the distance. So we allow this multiplicative factor here to say, okay, if you take a metric and you multiply it by 5, it's really not introducing any new geometry. And the least such d is denoted, is called the distortion, is denoted by c sub n of m. So this is the target, sorry, this is the domain, this is the target, and if I take my target space to be LP, by which I always mean LP of the real line with the Lebesgue measure, no funny one, etc. Whatever, we write Cp of m for C and P. Okay, this is going to be some short implementation we use, and in fact, so this is the definition of bi-Lipschitz distortion, and in fact, I mean, mostly we're going to be interested about embeddings in LP spaces, but a lot of the things that I'm going to say work a lot more generally.
Only one dimensional. It's only in dimension 1.
They're all isometric as Banach spaces, so LP of R is isometric to LP of R2. It's so if something embeds into LP of R, it's really the same. Yeah. So because of that, it can be LP of Z1, LP of 1000 measure. Okay. So and the point is, how will we be able, in principle for these lectures, to get lower bounds for quantities like this? So how will we be able to show that metric spaces actually do not embed nicely into LP or other spaces? Okay. And to do this, let me tell you to show you there's sort of a universal method, which again, in the end is going to depend a lot by the graph at hand. Let me tell you what's the dual formulation of bi-Lipschitz embeddings.
Alexandros said if both are linear spaces, then S should be sphere. But how we should think about S?
Nothing. It's completely irrelevant to the conversation. So if the target is a Banach space, you can always rescale your function and you take S to be 1. Okay. But if it's not, then it might be. But yeah, so S is not going to play a role. So here is the dual formulation of bi-Lipschitz embeddability. I'm not entirely sure who to attribute this to, so it definitely played a very important role in a paper of Lineal London Rabinovich from '95. This formulation that I'm going to write now is due to Matuszek a few years later, but I'm also sure that people knew this before. So okay, and it's going to be about really embeddings into LP. So given a finite metric space and the bi-Lipschitz distortion Cp of m is the largest d. Observe there it was the least d, now it's going to be the largest d, such that there exist two positive measures alpha and beta, which are defined on m times n, such that two axioms hold. First of all, every function f from m into, actually no, every function f from m into the real line satisfies the cofollowing Poincaré inequality if you take the double integral on m times n of the absolute value of f of x minus f of y to the p with respect to the measure alpha is bounded by the same thing with respect to the measure beta. Okay, so this is some almost abstract nonsense, right? Yet, if you try to compute these averages, not for the image of f, but for the actual distance of the metric space, so if you compute the average distance between x and y with respect to the two measures, this is greater than d to the p So this is a dual formulation. Let's read it together. So every function with values on the real line satisfies that it's the average distance between its values d alpha is smaller than the average distance d beta. But in fact, if you compare the actual distances on your metric space, you're going to be off by a factor of d to the p. And the power here skips for it. Okay, so this is a dual formulation of bi-Lipschitz embeddings, and it might seem a bit odd at least.
It does seem odd. So, given the embedding, is it clear what?
Yeah, I'm gonna get to that. Yeah. So there are two claims here because I'm saying if and only if. The first is that if you have an embedding, this cannot be done, and secondly, if this cannot be done, then somehow you can come up with an embedding. Okay, and as you can assume, one is more difficult than the other. So let's prove the easy direction. Okay, so assume that there exists a mapping, let's say F, a bit of a bad notation, but okay, from, call it content F, from M to LP, such that, as Sasha noticed, I don't have to introduce a scaling factor now because I can always rescale the function, right? So the distance between x and y is bound above by f of x minus f of y in LP is bound above by d times the distance between x and y, and also I assume also that this inequality holds for every little f now from m to the real line. Okay. So I'm assuming that I have a d bi-Lipschitz embedding, and I'm assuming that property 1 holds, and I have to prove to you that property 2 cannot hold. Okay, so that's good. So I'll start from the left-hand side, and I'll bound it from above. I have the double integral from n times n of the distance between x and y to the p. Okay, I'm not going to do anything imaginative, I'm just going to plug in this bound. So it's bound above, double integral f of x minus f of y, and p norm to the p, d alpha, right? And now I have an LP norm to the p. What is that? That's just an e.
You commented that we can take s equals 1.
Yes, because I can always rescale the function. So if a priori there is a function f, I can look at the function f divided by s, and it's going to satisfy that.
Then why didn't you include that in the definition?
Because that was for metric spaces. So if n is not a metric, if n is a Banach space, but for the most part, it's in Banach spaces. So here I have an LP norm to the power p, so that's just an integral, right? So let me just do this. So this is, and I do a Fubini. So I have an integral of r of a double integral, this is on n times m. Now each f of x was a function, right? So here what I have is the function f of x evaluated at the point p minus the function f of y evaluated at the point t to the p d alpha xy dt, because my LP was just LP of r. So now I'm gonna, this capital F of x is a function little f, so I'm just gonna apply inequality 1. So by applying inequality 1, I'm gonna get the same exact thing with alpha replaced by beta, and then I can apply the same Fubini. Okay, I'm not gonna rewrite it, so let me just write here double integral on n times m. What I'm going to have is capital F of x minus capital F of y, LP norm to the p d beta of xy. And now there's nothing left to do but just reapply this condition, right? So reapply the bi-Lipschitz condition. It's boundable by d to the p times what we wanted, which implies the two tails. Okay, so but this is sort of the easy part of the theorem, right? As you can guess. Now, let me just try this. Let's see if this is as easy as you've already seen. Okay, so I leave it there so that you can digest for a bit while I erase. So this is the easy direction, right? So for the difficult direction, what would you have to do? You would have to say that if a bi-Lipschitz embedding does not exist, then there is a way to find these two measures. Okay, and I call it duality. That's not sort of an accident. This is an application of Hahn-Banach separation. So this is an application of, hyperplane separation. You're gonna have to realize the two positive measures as a hyperplane on the space of matrices. Okay. So I'm not gonna do this proof, but in fact, the thing that we did now is something that we're gonna do several times in these lectures, which is to find a suitable Poincare inequality, like inequality 1, whose validity precludes the embeddability of a space M into the target space X. And the argument which we did here, let's say the easy part which I just proved to you, does not require the target space to be LP. In a way, the only place where I use that the thing is LP is that in 1 I assume the validity of the inequality for scalar value functions, and from this I deduce the validity for LP value functions. But if a priori we knew that inequality 1 used to hold for x value functions, then automatically you would deduce nonembeddability in x. So the only point that LP was used was that real valued implies LP valued if everything is raised to the power. Okay. Any questions? Okay. So I won't prove the converse, but again, the plan is to implement this kind of program for various classes of graphs. Okay.
Are you going to prove the converse?
No.
That's not the duality, so this is a weak duality and the other is strong duality.
It's really Hahn-Banach. It's a nice exercise. You take the cone of all matrices which bi-Lipschitz embed. Sorry, you look at the distance matrix, you take those which bi-Lipschitz embed so that they satisfy the bi-Lipschitz condition. I erased it now. And if something is not there, you can find the separating hyperplane. You write down what the separating hyperplane is. Some coordinates are positive, some are negative. You separate into positive measures. Okay, but the details can be. And so we're going to implement this program for various families of graphs. So the plan right now, if it works out, is to start with expanders, to discuss then Hamming graphs, to discuss infinity grids, trees, and diamonds. So probably that's more than I'll actually have time to do, but let's get started with the expanders, which is sort of a special story. So let's say expanders. Spectral. So I didn't want to assume that everybody knows what an expander is, so some people might be like bored for the first 10 minutes or so. Okay, so let G be a deregular graph. By which I mean a graph on which every vertex has d neighbors. All of my graphs are connected. So the Ziegler constant this is the following quantity. It's also called conductance, edge expansion. So it's something which I will denote by h of g. It's the minimum of the following ratios. So it's on the numerator, I have this quantity which I will denote by Es as complement divided by the cardinality of S. Now here S is a subset of the vertex set of size at most a half, of density at most a half, and Es as complement is a set of edges in the graph such that one of the endpoints belongs in S, and the other endpoint belongs in S complement. Okay. So here you just measure the proportion of edges. I'll introduce slightly different normalization, sorry. I'll introduce a factor d here. Okay, so I should say a deregular graph has dn over 2 edges. So if you think of d as a constant, such a graph has a somehow proportional number of edges to a number of races. And here you look at the proportion of edges which are leaving S for the complement. And you do it only for small subsets because the numerator is invariant under taking complements, so you want to avoid taking S in complementary. So the definition is that given a fixed number D, a family Gn of deregular graphs, the size of whose vertex set is going to infinity, is an expander graph sequence if there exists a positive number eta such that for every n, the Ziegler constant of dn is bound below it. Okay, so a standard graph sequence is a sequence of graphs which are growing and growing in size, yet these constants always stay large. What this means is that no matter which way you partition your graph in two pieces, you're going to be able to find a lot of edges joining one side to the other. Okay, so these objects, on the one hand, they're deregular, which means that they're very sparse, so they don't have many edges in general. They have a constant times n edges. But nevertheless, if you want to break them into pieces, you are forced to have many edges going from one side to the other. Okay, so they're sparse but very well connected. And the fact or theorem or proposition, theorem is that they exist. Okay, so expander graph sequence is something which we understand well by now. So this object exists. A random irregular graph is going to be an expander as n goes to infinity with high probability, in the sense that if you try to estimate the trigger constant of a random irregular graph, it's going to be a constant number. There are many things about this which are known, but for us we will care that these objects exist, and we will also care about the fact that they have an interpretation which is more analytic rather than combinatorial. Okay, are there any questions on the definition?
So the trigger constant is some sort of isoperimetric constant.
Exactly. That's exactly where we're headed.
And it's stable in some way. I mean, this in expanding it doesn't become.
What do you
this
mean?
Expander graph sequence, like it cannot become too small in some way.
You mean the constant?
Yes.
Yeah, the constant has to be constant. Yeah. So this is bounded above by universal constant also because the graph is irregular, but this says it's also lower bounded by constant. Yeah, so it really has to remain constant. And they very famously have an algebraic or analytic, in my opinion, interpretation which goes towards what you were saying. So let me say a few words.
Alexandros, you mentioned some phrase that something was sparse. Where is sparseness?
Oh, sparse in the fact that the graph is irregular. So I mean, in principle, it could have up to factor n squared edges, but it only has linear.
If it's not sparse, it would be very easy to.
Exactly. Yeah. So you can take the complete graph. But it's so if you want your graph to be connected, you need to have linear number of edges, and somehow this is. Yeah. So let's speak a bit about algebra. So let AG be a normalized adjacency matrix of G. So AG is a matrix who's indexed by the vertex set. So if you take UV two vertices, then this is equal to 1 over D if U and V are connected by an edge, and 0 otherwise. So U and V here. And the fact, I mean, this is a row. The fact that the graph is irregular tells us that this is a row stochastic, also column stochastic as it's symmetric matrix. So the fact is that, so here in the next word, so AG is row stochastic. And then this, of course, imposes some condition spectrum. And let you think about what it is when they do this. Okay, so AG is an averaging operator, right? So all the eigenvalues are between -1 and 1. When we made the schedule for the school, we left an extra 15 minutes per lecture for questions, but now I know it's 15 minutes for racing. Okay, so, its spectrum is, well, the largest eigenvalue is 1, so if you take AG and you multiply it by the all ones vector, you are again going to get the all ones vector because it's row stochastic, so the largest eigenvalue is 1. So there's a second eigenvalue. And the last one, which is the size of the vertex set, is going to be greater than or equal to -1. So, this is G, and I use so lambda I of G is lambda I of the adjacency matrix. Okay, so I the 2. And the important quantity here, so there are more than one important quantity. So even the last eigenvalue encodes the effect to which the graph is bipartite, but for us, the quantity, the gap between the first and the second eigenvalue is called the spectral gap. So the spectral gap is the jump that you have between the first and the second eigenvalue. And the constants, the connection to expansion is what's called figures inequality for graphs. Which is not due to figure, equal long minimum 5. So they proved that for every G which is deregular, notice that the degree of regularity is incorporated in my definition of the Jigger constant. So for me, all the graphs are going to be regular, even though it doesn't play statically grow. So the Jigger constant of G is bounded from below by the spectral gap divided by 2, and it's bound above by square root of 2 and the spectral gap. Okay, so you're like that word, thank you. Okay, so it's bound above and below by 2 functions of the spectral gap. Everything here is sharp, the square root, the numbers, everything is sharp. Examples where this is a thing, but what does this mean? I mean, qualitatively, we said that a graph is an expander if this quantity is a universal constant. So it being a constant is equivalent to the spectral gap being a constant, since it's bound above and below by these 2 functions, right? So qualitatively, Vn is an expander sequence if there exists a different number, let's call it delta, such that the spectral gap is bounded below by delta for everything. Okay, but by qualitatively I mean that eta there and delta there not directly. Okay, so being an expander is also encoded very well in the spectrum in how far this first and second eigenvalue are. Okay, and apologies again to the people who knew all those things, but they have to be mentioned. So let me rewrite this property now. Are there any questions so far? Sorry. Let me then rewrite what I just said in the form of a functional inequality. So here's a lemma. So let G be a deregular graph. And I speak about a constant in a certain Poincare inequality, so the least constant gamma is gamma of G, such that any function from the vertices of the graph into N2 specifically satisfies that the average over all vertices is invisible. Am I right here? Not so much. Sorry. So that the average over all vertices of f of u minus f of v and 2 norm square. Now remember, f of u is a function. Is bounded above by gamma over the average over all edges of the same thing. F of A is f of B is equal to 2 times the spectral gap, all raised to the power minus 1. Okay, so let's adjust this for a second. What is, again, speaking a little to the analyst, but everybody here knows this. What is the Poincare inequality? It's about bounding a variance by differences over edges. Okay, and here what you have on the left hand side is very much the variance up to a factor of 2. And here you take the sum or the average, but it doesn't really matter because the graph is irregular, to the difference between a point and all of its neighbors. Okay, so if you fix your A here, B is running over all the neighbors of A. So this is really, I mean, the Poincare inequality on this graph. And the best constant here is the reciprocal of the spectral gap. So saying that a spectral gap is bounded from below, which we agreed is equivalent to expansion, is equivalent to saying that the graph satisfies a Poincare inequality with a universal function. Now the proof is linear algebra. Do it. I can say it's really linear algebra. I mean.
So these are these two measures which you mentioned.
Exactly. So that's where we're heading. So here, I mean, you see again that there are two measures. One is the uniform measure, thank you, over the uniform probability measure over pairs of vertices, and on the right is the uniform probability measure over edges. Okay, and we're going to see right away what this means in terms of embeddings, but let me just say a word about the proof. Somehow, the first remark, and then we're doing it left and right from now on, is that again, when you have an inequality for a 2 norm to the power 2, it's equivalent to look at the same inequality for scalar values.
And L2 doesn't matter, it's just complex numbers, right?
Exactly, that's what I'm
It's the
saying.
same thing.
Exactly, that's what I'm saying. So it's completely equivalent. The constant here is going to remain the same if I just look at the scalar value inequality. Why? Because you just sum up over it. So before, same constant for scalar value. I follow the Val's ideology of scalar being real. You shouldn't take credit for that. and okay, and without loss of generality, let me just also assume I can add and subtract a constant that the sum over u of f of u is equal to 0. Okay, so this means that f, if you view it as a vector, is orthogonal to the first eigenvector of AG, since the first eigenvector corresponding to the eigenvalue 1 is the all ones vector. Okay. Okay, then what is the left-hand side? Well, the left-hand side is very easy to compute, and you have really no L2 norm squares. So f of u minus f of v, you're going to expand the square, is just 2 times sum over u of f of u squared, and here you take normalize by the size of the vertex set, so you just expand. And the right-hand side, so what is the right-hand side? You have this normalizing constant 1 over the size of the edge set. So this is 2 over d and the size of the vertex set. And here you're going to have a sum over a and b. So we're going to have f of a squared plus f of b squared minus 2 f of a f of b. I'm just expanding the square. And here it's a sum over edges, but I'm going to write it I'm going to introduce here the adjacency matrix of the graph. Okay, so this is going to be AG, the point AB, and now A and B are arbitrary vertices. And the only place where I lost is that AG was normalized. So this factor of P here is absorbed over there. Okay, so I'm just plugging in what the adjacency matrix is. Okay, just plugging in the 0, 1 over D value. Okay, and now this matrix is row and column stochastic. So when I sum over B, AG, AB, f of A squared, the sum over B disappears. So what I'm going to have in the end is just a sum over the f of A squared, a sum over the f of B squared. Okay, sort of messing up. So it's 4 over the size of the vertex set, because this thing is going to be the same. And here I'm going to have sum over, it should be A f of A squared. I just changed the notation again to make it look like the left-hand side. And then here we're going to have the sum over U and V, A, UV, f of U, V. Okay, so I just rewrote everything. So equivalently, if I just solve for this quantity on the left, so remember that the right-hand side is multiplied by gamma. So if you just solve for that, let's say star. So star is equivalent to the claim that the sum over U and V, AG, UV, f of U, f of V, is bounded. Let me tell you what the constant is. It should be something like 2 gamma minus 1 over 2 gamma. And then there's going to be the sum over U of f of U squared. Okay, so I'm just plugging in the left-hand side and right-hand side, and I'm solving for this, which is the only mysterious quantity. I'm not doing anything, okay? So I want the validity of this inequality for which f? For every f which is orthogonal to the all-one vector, which is the first eigenvector. Okay? So this forces the constant here to be the second eigenvalue. Okay, so this is AFF bounded by f squared. And I want this to hold on the orthogonal complement of the first eigenspace. So this forces 2 gamma minus 1 over 2 gamma to be the second eigenvector of G. And that's the proof. Okay, so as I promised, it's really just linear algebra to check that this is the best constant. Any questions on this computation?
So this also holds if you have trivial gap, right?
Can you see?
This also holds if your gap is trivial, 0.
If the gap is 0, I mean, yeah, because you are going to put the constant is going to become infinity, but if you put on the other side, then yeah. Okay. Okay, so again, remember we have this philosophy about embeddings that if we want to prove nonembeddability, there exists a correct pair of measures, or as we say, a correct invariant, which is a function of inequality. And let me show you now the consequence of that, which is a consequence modulo the non-trivial fact that these objects exist. So here is the theorem. It's originally due to Milan, London, Rabinovich, famous paper 95. But this proof is due to Matuszek. So for an expander G and vertices, maybe I should write for a deregular expander, sorry, for a deregular expander G on n vertices, we have that C2, so the Euclidean distortion of the expander with the shortest path metric is at least a constant times log base Euler. Okay, so if you want to embed a deregular expander on n vertices, by the way, this terminology is going to come. What does it mean to have an expander on n vertices? It means that it's a deregular graph on n vertices, and I'm just thinking of the spectral gap as a constant. Okay, so the spectral gap appears everywhere in the estimates. I'm just thinking of it as a universal constant. Okay, because formally we define an expander graph sequence, but just a member of an expander graph sequence.
I forgot these notations. What does that mean?
A very quick question. If it's not exactly irregular,
Yeah.
does the argument still work?
Yeah, everything is going to work. If it's, I mean, everything we do throughout is also, you can also do it for an arbitrary sort of Markov chain with this kind of thing. You can, rather than the random walk on the graph, you can have a general Markov chain, and all of those things are going to make sense. But then here, rather than log base D, you're going to have some quantity which depends somehow on the Markov chain. But yeah.
Just the reason I'm asking, because there are natural families of standard graphs which are not exactly irregular,
But they slow very, they grow very slowly, the decrease. Yeah, yeah. So all those things can be. So if D is, say, log n, this bound is meaningful. Log n over log n.
So expander doesn't want to be embedded.
Exactly. And we've seen a bit in the worst possible way. So an expander cannot be realized in any reasonable way inside Euclidean chain.
So when you mean taking the Markov chain, do you mean taking the random walk on the complete graph with some weights, and then you just mean that the weights satisfy?
But really have a general Markov kernel, general stationary measure. You can, I mean, all we did was linear algebra, so it's in a way everything really works. Yeah. Any more? Okay, so let's see this proof. It's very easy. So suppose F from the vertex set where 2 is a d by Lipschitz. Embedding. As I won't write the condition again, so the lower bound is with constant 1, the upper bound is with constant capital P. So again, we don't need the scaling factor S that we had before because it's with values in the Banach space, right? Okay, so then applying inequality star, which is up there, right? Miraculously numbered it. So we have. I'm just gonna reapply the non-embeddability proof from before exactly as is, right? So 1 over the size of the vertex set squared the sum over u and v vertices of the distance between u and v squared is bounded above by the bi-Lipschitz condition by the same thing with f of u and f of v. Okay, so this is the lower bound of the bi-Lipschitz condition. Then I'm going to apply inequality star with gamma being a universal constant. So here I'm putting this sign for a universal constant, so it's bounded by 1 over the size of the edge set. The sum over all edges of f of a minus f of b squared, so this is edge. So this is because of star. And then I'll apply the upper Lipschitz condition. So this is bounded above by d squared over the size of the edge set over a sum over all edges of the distance in the graph between A and B squared. But now what is the distance on the graph between A and B? Well, they're connected by an edge. So this distance here is just 1. So it's an average of ones, it's just 1. So this is d squared. So what we get is that d squared is greater than the average distance between 2 points on the expander. Okay, so what I have to do now is that I have to estimate this quantity. Are there any questions? So here and here, I'm just applying the bi-Lipschitz condition. Okay, I'm repeating exactly the same proof I wrote before at the setting of general measures. I'm just applying it very specifically for the left being the uniform measure over pairs, and the right being the uniform measure over edges. Okay. And all I have to do now is estimate this average from the okay. So let's do that. So fix the vertex u. Now, if you look at the ball of radius k around the vertex u, okay, since the graph is irregular, this cannot have many points. So at radius 1, you're going to have at most d. At radius 2, with a very bad estimate, you're going to have at most d squared, and so on. Okay. So the ball B R at u has at most d to the k points, d to the r points. So for r being, say, the floor of log base d of n over 2, at most n over 2 points. Okay, so you can go up to this radius, and you have at most n over 2 points. So here is your graph.
Who is the capital L?
That's the floor.
The floor function. The smallest integer below.
It's not.
Yeah. So you have u, you take here this radius r, and you have at most n over 2 points inside, which means that you have at least n over 2 points outside. Okay. So the average so now u is fixed. The average of the distance squared between v and u, so there are at least n over 2 points here, so it's 1 over n. There are at least n over 2 points, for which the distance is at least r. So here I'm going to have p of n over 2 squared. So this is, just to stop writing these things, this is at least log base d of n squared up to universal constant. So this is something which I have for every u. So when I average over u as well, I deduce that the left-hand side here is bounded below by log base d of n squared. And that's the end of our proof, because the left-hand side is log base d of n squared, the right-hand side is d squared, so capital D squared, so capital D has to be greater than log base d of n. So really, I'm just reapplying exactly the same proof that we had before in the abstract dual formulation, but the measures are given, and I can actually compute the quantities, right? The part 2 if you want. Okay, and before we wrap up with expanders and move on to something else, so why is this log n bound exciting? Because there's a very deep theorem of there's a theorem of tremendous importance, let's say, which is Bourdieu's embedding theorem from '85, who proved that any finite metric space has Euclidean distortion at most log the number of nodes.
Isn't it L1?
L2 is better than L2 embedded. So so any finite metric space embeds into L2 with distortion log the number of points, and expander graphs actually saturate the bound. Okay, so we proved that this bound is sharp for expanders. That was in the paper in the London Rabinovich, there was an algorithmic application of actually how to compute efficiently the Euclidean distortion, the writing the dual program. So it was coming from elsewhere, but one of the main contributions was also that they managed to find exactly the Euclidean distortion of expanders and to prove that the log n is sharp, which was not known. So Bourdieu had given a lower bound of log n over log n by looking actually at random graphs, which are expanders, but by looking directly at random graphs, he was losing a log n factor. Okay, so expanders in this sense are the least Euclidean finite metric spaces. And even to date, I mean, almost all the spaces we know that saturate the log n bound have some sort of expander-like behavior. Are there any questions?
Are you going to unite this and that, or it's useless? Or
This
why these two things together? You want to
just to show that this is that this cannot be improved, for instance. So by getting a log n bound, I wasn't lazy. I did my job well. Yeah, that's the best thing you can do for absolutely anything. So that's all. And of course, I'm much slower than I thought I would be. So maybe I won't jump to another thing today, since we have maybe 10 minutes or a bit more. I'll just speak about LP distortion. So, in principle, here we use the fact that we had power 2 extremely heavily, right? In the proof that the best constant in that inequality was 1 over 1 minus lambda 2, this was proper, like very heavy, not heavy, like linear algebra. So it was really linear algebra. We expanded in eigenvectors and so on. And in principle, we're going to see examples here where in this course, I mean, where the power matters a lot. It's not that because you have an L2 inequality, you're going to have an L4 inequality. But there's a very special feature of expander graphs, which is the regularity, namely, which makes the power irrelevant. Okay, and this was something which, first of all, is also encoded in Schigger's inequality, because the Schigger constant, is in fact the best constant in an L1 inequality rather than an L2 inequality. But as is, it was formalized by Tushek. So let me just tell you the best thing that's known now, which is the vector value. Tushek. No reason really to state the vector value, but extrapolation principle scalar valued form of that is due to Matushik in 87. This is due to Kim Delat and Michael de la Salle. I want to say in 2017. I think. Okay, so let gamma of G with respect to a norm now, any norm to the power P is required. Oh, be the least constant gamma such that any f from the vertex of the graph into this norm space satisfies the LP analog of the inequality star which I just erased. So it's 1 over the size of the vertex set squared, sum over pairs of vertices, f of u minus f of v. Now, this arbitrary norm, power p, is bound above by this constant gamma, not raised to the power p, for this normalization. F of a minus f of b to the p. Okay, so rather than scalar value or L2 value, they take an arbitrary norm space, and rather than power 2, I put power 2. So then, for two numbers p and q, p is smaller than q. All these constants are polynomially related. So the constant of the inequality with power p is bound above up to multiplicative constant depending on p and q by the constant with power q. And it's bounded below, again, multiplicative constant depending on p and q by the power q constant to the power p over q. So this is, so yeah,
So who is X here?
X is the target space.
Is what space?
It's a target space. So
Just any linear norm space?
any norm space.
Any linear
No matter any norm space. This is recent, so the fact that you can go to any norm space is recent. Okay, so this is a very special feature of the fact that you have a regular graph. So in the sense that on the right-hand side, the sum over edges that you have is normalized. So if you take the hypercube, it's just false. It's not true that you can have an inequality in the hypercube like this with power greater than 2.
Hypercube is also regular.
Yeah, but there are dependencies on. Sorry. The way we usually state the Poincare inequality in the hypercube is that on the right-hand side you have a sum over edges. So it would be an average over edges, but the constant would be n. So this n is going to be multiplied by it's going to be n to some power, and suddenly this is not a useful inequality. So it stops being dimension free when you.
Okay, so what's important is that the degree is constant.
What's important is that the way the constants appear here, this sum is normalized. So the degree can be n. This is true for the.
But then you'll have.
Yeah, so there is no dependence on d in these bounds. Yeah. So this part is okay. So there's no dependence on d. It's just that the way the constant is defined is defined with respect to the normalized version of the epsilon. Okay, so corollary, if you want, and that's exercise. The LP distortion of an n vertex expander is bounded below up to a constant depending on p by, again, log-based derivative. Because you have exactly the same inequality. So, I mean, if you saw, we didn't really use power 2 that much. I mean, there was a counting argument there, but the power 2 up there wasn't really used. So, it's always log-based d of n. In fact, if you want to be more careful, you can show that it's log n over p. And then, so if you want to track the dependence on p in a good way, it's log n over p. And in fact, from Bourdieu's embedding theorem, if you do it very well, you can get log n over p in the upper bound. So dependence on p is also well understood. But we won't get to that. So this, I just want to point out, there's a very special feature of regular graphs that you can pass from a 2 to and then, so just to close before we'll continue in the afternoon, but the next goal is to study Hamming graphs. We're going to speak about an infinity grids. So you're going to take the set of integers from 1 up to n with infinity on, infinity grids. We are going to look at diamond graphs, so fractal constructions, and hopefully. Okay, but the issue is that I kind of want to, I mean, so far, I only proved L2 nonembeddability for you, and I told you without proving that LP comes for free. But in fact, I mean, in principle, we care a lot about LP embeddability, and there are many reasons to care about embeddings into spaces other than L2. So before we get to that, I will need some preliminary Banach space theory notions, which in fact are, for the context of LP spaces, are all classical inequalities from the 30s and the 40s, but all of our theorems are going to be proven with certain Banach space assumptions that I'm going to explain this afternoon. Okay. Thank you.
What kind of distance we have?
So on the Hamming cube, we have the L1 distance. So it's the
Usual white, right? Or the graph distance.
So this is the L1 distance. This is the infinity distance. Why?
Why?
Because it's, so with the L1 distance, the moment you take m equals 1, it captures all the interesting geometry. So if you want the, so if you look at the Euclidean distortion of the hypercube, but this is a theorem, okay? With the L1 distance, this is the same number exactly as the Euclidean distortion of all of our n with the L1 distance. So if you want to embed the hypercube into Rn, there is nothing better to do than, if you want to embed the hypercube into Hilbert space, there is nothing better to do than embed the whole Rn. So taking a larger n here for the L1 distance doesn't play a role. Taking though n equals 1 for the L infinity distance, I mean this is just all the distances are 1, so this embeds very, very well in Hilbert space, it's just a simplex. So, this is going to appear in the proofs that somehow in L infinity embeddings, or more generally in LP for p bigger than 2, the size of the scale here actually plays a role. This is going to be a theorem. And there's a threshold at n equals root n, things start becoming interesting there, so I hope I'm going to get to that for the afternoon.
Any questions? And then there, how do you change from 2